Yeah, today I'm going to talk about particle-soliton dualities and S and T dualities, which I already said something about yesterday, but today we'll go in more detail into that. So a brief recap on duality, the notion of duality that I introduced yesterday. I had this formal schema where dualities, regardless of interpretation, so just formally, we say that duality is an isomorphism between two model triples, right? And a bare theory is given by a set of states, quantities, and dynamics. So that's what I mean by a triple. And then, so given two such triples of two models, M1 and M2, that are triples, we have a duality if there is an isomorphism, which means that there's an isomorphism between the states of the two models and also between the quantities. And this isomorphism should be such that the values of the quantities match. That's of course something that we want for a physical theory, that the values that we calculate of all the physical quantities will be the same, the actual numerical values. And also that it should be equivariant for the two triples dynamics. So there is a commuting diagram between the duality and the dynamics on the two sides of the duality. And I also emphasized the analogy or the close relation with symmetry. In some sense, the duality is a generalization of this notion of symmetry. Symmetry is also a map on or can be seen as a map on the space of states, but then a single space, state space, and then automorphisms on that space, on the state space, preserving the set of quantities. So now with dualities, we have two different spaces of states, which are nevertheless isomorphic under the duality. So as the general formal notion of duality, then we saw another type of duality, which is actually not a duality, strictly speaking, which is this notion of effective duality, which is an approximate instantiation of the idea of duality. And then we saw some important features and roles of duality when we interpret the duality. And so these are the features and roles that we will discuss today. So in particular, the notions of hard versus easy, micro versus macro, and notion of unification of various models, and also the notion of symmetry breaking. So today, when I do my examples, I want to illustrate some of that. So this is the aim for today. I will discuss three important examples of dualities, and then I will exhibit some of their key properties. So illustrating what I said yesterday about, in particular, the formal schema, but also this idea of effective duality and also the idea of self-duality that we discussed yesterday. And then finally, also the features and roles of duality that we discussed. So that's, and here is the outline of what we will do. I have 4 points. Particle-Soliton dualities is this first set of examples, then S-duality in quantum field theory, and then we will move on to string theory. I will first introduce what string theory is, and then discuss the dualities in string theory, and they say something about these effective dualities between string theories and M theory. So we begin with the first point of particle-soliton duality. By the way, if at some point you cannot hear me well or you cannot see me or whatever, just let me know. So particle-soliton dualities, and the two aspects that I'm going to illustrate there, that these dualities illustrate, are the aspects of hard, easy, and the aspects of micro versus macro. So I will discuss two examples, the Sine-Gordon theorem duality, which is a generalization of the bosonization that we already discussed yesterday, and also the 't Hooft-Polyakov monopole, which has been quite important in quantum field theory in the past 40 years or so, 50 years actually, and which will play a role in the discovery of deep brains in string theory and so on. So Sine-Gordon theorem duality. This is like I said, a generalization of bosonization, where now we have a more realistic model, because now we have not a free field theory, but we have a field theory with a potential. So if we look at the bosonic model, the Sine-Gordon model is called Sine-Gordon because there is this sine kind of potential. It's actually a cosine, but in the equations of motion, it comes up as the sine. So it's a highly non-trivial and non-linear field theory. Now in the classical, and actually if you expand this potential, you see that there is this -1, because if you expand the potential for small phi, then the leading term in the cosine is of course 1, so that constant just cancels. And then the next term is the quadratic term, which gives you the mass. So the first term in the expansion is the mass of the scalar field. So it's now no longer a conformally invariant theory. There will not be conformal invariance in this theory. And then the next term in the expansion will be a quartic term, which is a phenomenologically interesting term because it's a term, it's the first non-trivial interaction that we can add after the mass in a quantum field theory. But we will be interested in the whole thing, including the cosine. So, yeah, normally what we do in perturbative field theory is what I just said. We do a perturbative expansion. We assume that the scalar field is small, and we look at a perturbative expansion around the vacuum phi equals 0, and then we look for the spectrum of perturbations around that vacuum. And that tells us what are the particles, what are the particle excitations in the spectrum, what is their mass, and so on. Now we are going to do something slightly different because we are interested in the non-perturbative features of this theory. And so we are looking for the vacua of this potential that contain non-linear solutions. So it's not enough to do the linearized approximation. And the reason we want to do this is because we want to get at the notion of solitons. And solitons are defined as, solitons in field theory, are defined as smooth finite energy solutions of the nonlinear equations. Okay. So the first requirement is that the energy is finite. And to kind of simplify, we're going to consider static solutions. Later on, you can generalize this. You can boost the solutions to give them a speed. But for now, we take static solutions. So this is the energy. This is what the energy looks like. We are again in 2 dimensions, 1 space and 1 time dimension. So it's fairly simple from that perspective. So there's the energy we only need to integrate over x. So for the static solutions, the first term, the kinetic term, is just 0, and this is what we get. And this is a manifestly positive definite quantity. Now you see that we have an integral from -infinity to infinity over the whole space. If we want the energy to be finite, then we need to require that the field goes to 0 at infinity. That's a reasonable solution if you have you want a reasonably, I mean, it could be exceptions, but if you want a reasonably well-defined solution at infinity, that's a sensible solution, a sensible way to impose that the energy is finite, to impose that the field goes to 0 at infinity. That since both terms are positive definite, this means in particular that the potential needs to go to 0 at infinity. So we look for zeros of the potential. Okay. So that imposes, in particular, if the potential needs to be 0 at infinity, that means that since the potential has this cosine, the cosine needs to be 1 at infinity. So the zeros are discrete. They're these zeros of the cosine 2 pi n divided by beta. Beta is this beta over here. So you see that you need to look for when that is going to give you 1. So we can plug those solutions. So those will be our asymptotic values. And using the equations of motion, you can actually rewrite this in the following way. That's 2 lines of mathematics, algebraic derivation. This is the result, and this is an integral that you can actually carry out exactly, and this is the result. So the energy for these vacua that are static, that's the value of the energy. Now, in 2 dimensions, you can define a conserved current that is not a Noether current. It is defined in the following way. So it's with this epsilon tensor, this antisymmetric 2-dimensional epsilon tensor, and then the first derivative of phi. This is something that you can write down in 2 dimensions. It is conserved in the following, well, it's conserved in the sense that its divergence is automatically 0. Its divergence is identically 0. And it is topological in the sense that to find the charge associated with this current, we only need to know the value of the current at infinity, precisely because there's a total derivative here. So if you calculate the charge associated with the current, so the integral over the 0th component of the current in the usual way, what you find is the difference of the values of the asymptotic values of the field at infinity. And that, using these solutions over here, that is an integer number. So you see that, so what do we have? We have a nonlinear field. We have found finite energy solutions of this field. These solutions are such that at infinity, the field goes to take some integer values, and then you can associate a conserved current with any such field. You can always define this current, and the charge, the topological charge associated with that field, turns out to be an integer that only depends on the boundary conditions on the field. So depending on what boundary conditions you impose on the field, the charge will take one value or another. So that's, in a nutshell, those are the sign-Gordon, what we call solitons. These are solitons because they are finite energy, nonlinear solutions of the field equations. And they are topological in this sense that they really depend, I mean, their main properties like the energy and the charge really just depend on the asymptotic value, not on the local dynamics. Now, so we have a duality between this sign-Gordon model and our theory model. So now we are going to look at the other side of the duality, the theory model. So the theory model is a generalization of the free fermion that we saw yesterday. The free fermion that we saw yesterday is just this this first term here in the action. But now we also have, now we also have the mass, and we also have a quartic interaction. This psi to the 4th power with some gamma matrices. The details are not really important. So that's our theory model. It has a global U1 symmetry. Notice that our model yesterday had a chiral symmetry. This model does not have chiral symmetry because of the mass term. So the mass term breaks the chiral symmetry. We still have a global U1 symmetry. So you can make a constant phase shift of this fermion because we have everywhere we have fermion bilinears with psi and psi bar. So this constant phase will disappear. So that's a global U1 symmetry. And there is a conserved Noether current associated with that symmetry, and it takes this form. Okay. So now we claim, this is what the literature has done showed that there is a duality between these two models. And this duality is bosonization. It's an extension of what we did yesterday. And it exchanges these two currents in the similar way to how yesterday we also had a match between two currents. So it exchanges this neutral current that I just discussed with the topological current of the bosonic mole. And to do that exchange, you also need to exchange the coupling constant. So this beta, beta squared that is in the sign Gordon mole needs to be mapped to G. So G is the coupling that appears in the quartic term, quartic interaction. So you get 1/1 plus G, and then there's, I've inserted temporarily H bar just to see how things depend on Planck's constant. I will not prove this result is an extension of what we did yesterday in some sense. So I will ask you to take it, to just take it for what it is. And I can give references if people are interested. I want to mention several properties of this map. So one is that it shows the hard-easy property that we discussed yesterday. So when we are at weak coupling in the sign Gordon mole, so beta is small over here, that means that G must be large on the other side. And the other way around. If beta is large on the bosonic side, then G must go to a finite value. It must be of order 1. Sorry, it must be actually if beta is of order 1, which means that it is strongly coupled, right? Then G is of order, it goes to 0 in the sign Gordon mole, in the theory mole. So it is a weak, strongly coupled duality, just like we had yesterday. Only the algebra is slightly different. So this duality, in effect, allows us to describe the fermionic excitations of the massive theory mole in terms of a soliton that is a superposition of coherent states phi. So it's quite similar to what we did yesterday. So what I'm saying is that if we have this, if we match one of these solitons, which have these integer values, those actually correspond to usual neutral currents that are at weak coupling. So if beta is of order 1 here, then G will be perturbative. So the usual fermionic weak coupling fermionic excitations that we have in the fermionic theory correspond to these solitons that are at coupling 1 in the bosonic mole. So in this sense, we now see here quite explicitly how a weakly coupled weakly coupled particle problem corresponds to a strongly coupled solitonic problem on the other side. Coleman in 1975 wrote that the particles which are fundamental in one description are composite in the other. So in that sense, I'm not going to go into the details of this now, but that you can see this is an expression of this idea that there is an elementary versus solitonic, the duality exchanges elementary versus solitonic quantities, or that there is a micro versus macro perspective, in the sense that the micro, if we regard the micro perspective as the weakly coupled one, while the macro perspective is this coherent state perspective. Okay, those are matters of interpretation. So what is the significance of this? So like I already said, it illustrates those 2 points. And also from a physics standpoint, these two features of bosonization, they can be generalized to other dualities in quantum field theory and string theory. So these are quite general features of this type of duality in more complicated cases. For example, the particle vortex duality that you have in 3 dimensions. In 3 dimensions, you have that these solitons are vortex type solutions. In 4 dimensions, you typically get electric magnetic duality for quantum field theories, and then S duality in string theory, and all of them show these features, these two features of hard, easy versus and elementary versus solitonic. I mean, I don't want to say that these are kind of universal features of duality or something like that, but in the actual examples that we find, the advanced examples that we find in string theory and in quantum field theory, we do find these two features illustrated. Now, to kind of make that leap towards that more advanced physics, I now want to discuss as a kind of intermediate step the Etov-Polyakov monopoles, which have been instrumental throughout the late 70s and 80s and early 90s in developing the kinds of technologies that people have used to discover dualities in string theory. I would say that the discovery of dualities in string theory would have been almost unthinkable without going through all these steps of studying solitons in low-dimensional field theories, in condensed matter physics, and also in particular the Etov-Polyakov monopoles were very instrumental in those discoveries. So of course, we all have encountered at some point in our undergraduate studies the idea of the Dirac monopole, that we have electric magnetic duality in Maxwell theory, and that we can generalize that to include electrons if we somehow can make sense of this idea of the Dirac monopole. Now, the Dirac monopole is well known to be incompatible with the existence of a smooth, globally defined vector potential, because the vector potential cannot be defined. You no longer have a Bianchi identity, and so the vector potential simply is not defined, at least not globally. Also, the Dirac monopole gives rise to a singularity in the field, so you can introduce it by a singularity. Now, both problems are resolved by going to a formalism where, rather than looking at a globally defined gauge field, you use the fiber angle formalism, where you have basically two vector potentials defined on two patches of your manifold, and you glue them together. That is one way to deal with that problem, but there is still another problem of the old idea of Dirac, which is that it's not a dynamical object. It doesn't, for example, it doesn't tell you how the Dirac monopole behaves, what is its dynamics, how to calculate its mass. This is something that is quite different for the Etov monopole solution, because that solution does arise. It arises as a soliton solution, as a smooth finite energy solution of the nonlinear equations of an abelian gauge theory. In particular, you can calculate its mass from the theory. So the theory gives you a way to calculate the mass, and also there is a dynamic for this monopole, because it is just part of the usual dynamics of the theory. You don't need to introduce it by hand through some singularity. Part of its significance is that it was proposed as a mechanism for color confinement of quarks in particular, as a dual mechanism of the condensation of Kupar pairs in superconductivity, so a dual Meissner effect. In the Meissner effect, you have pairs of electrons that condensate in the vacuum, and then thereby repel the magnetic field from the material. That's the Meissner effect. In this case, it's the magnetic dual of that. You get monopoles in the vacuum that attract each other through through magnetic string lines, and thereby the electric field is repelled from the color field, which is here the electric field, is repelled from the spacetime. This was verified by Polyakov and others in three-dimensional Yang-Mills 6 theory. So they verified that actually, and they did that in lattice calculations, lattice gauge theory, that is the actual mechanism for confinement in 3 dimensions. And later on, Seiberg and Witten showed that in 4-dimensional n=4 super Yang-Mills theory, that this is also the mechanism for confinement. Now, part of the significance of monopoles is also that n=4 super Yang-Mills theory is conjectured to have exact electromagnetic duality. Now we know that QCD, for example, does not have exact, it's not an exact electromagnetic dual theory. On the other hand, n=4 super Yang-Mills theory does seem to have that symmetry. And also the monopole exhibits many of the aspects of what we mean by a soliton. So here are some of the details, or some of the algebra that goes along with it. We don't really need the details of the solution, but just to show you where it comes from. So here at the top, we have the Yang-Mills, the Lagrangian for the Yang-Mills Higgs theory with gauge group SU2. That's the usual Georgite glacial mode from 1972, where you have a non-abelian gauge field with gauge group SU2 coupled to this Higgs field, which has a potential. The potential is the phi to the 4th potential for the usual Higgs mechanism. That's why I said earlier that the Sine-Gordon potential, the fact that the Sine-Gordon theory gives you the phi to the 4th potential is significant. Now, again, like we did for the Sine-Gordon theory, we look for finite energy solutions, which means that we impose that the potential should go to 0 at infinity. In particular, now there is also a restriction on the gauge field at infinity for the finiteness of the energy. That restriction is actually that the connection is flat. So the F mu nu is 0 at infinity. We have a flat connection, which means there's no electric field at infinity. The Higgs field, because so the potential has to be 0, but because we have this Mexican hat type of potential, so we have phi squared minus v squared everything to the 2nd power, where v is a constant. That means that you're going to minimize the potential not by setting the Higgs field to 0, but by setting the Higgs field to some constant. So phi is going to go to basically to v at infinity. So the Higgs field gets an expectation value at infinity. Here is the detail, this middle formula, the detail of the ansatz that goes into the Polyakov solution. Not really important, just to flash how that looks like. So it's a topology. So it's an ansatz that satisfies these requirements that we have here on top. So it's a topological. So the feature of the solution is that it's topologically non-trivial, because the Higgs is non-trivial at infinity, and it actually maps. You can view this Higgs field as a map from the 2-sphere at infinity. So at infinity we have a 2-sphere, and the Higgs field takes values in the Lie algebra of the group SU2, and SU2 is and within that algebra, you see that phi squared is v squared. So we have a sphere, we have a 2-sphere within the group SU2. So we have a map. So the Higgs field is a map from the spatial 2-sphere at infinity into the Higgs 2-sphere on the group manifold. Okay. So this solution has a zero electric field, as I already said, because it has the feature that the zeroth component of the gauge field just happens to be zero. That's part of the ansatz. On the other hand, it has a non-zero magnetic field at large R. I mean, the magnetic field does go to, to zero at infinity, but it goes to zero like a Coulomb charge. I mean, like a magnetic monopole charge. So if you integrate it over a sphere at infinity, it will give you a finite value for the charge. So this is a magnetic monopole at large R, and its charge G that you calculate. So you see that the magnetic field is written in terms of the electric constant. So if you calculate the magnetic charge by integrating the magnetic field over the two sphere at infinity, you actually, the numerical value that you get is actually satisfies Dirac's quantization condition for the electric and the magnetic charge. You can also calculate the mass of this configuration, and it satisfies the so-called Bogomolny bound. So the mass is larger or equal than V. V is the Higgs, is the value of the Higgs field times the magnetic charge, and it's larger or equal rather than just equal, because here we have a class of solutions. We don't have a single solution, but we have a class of solutions. So depending on which solution you have, you could be at the strict bound or you could be above the bound. At weak coupling lambda, the mass will saturate the bound. So when the coupling is zero, the bound will be saturated. So actually, if I remember correctly, I think I should actually correct what I just said, and because this solution is actually uniquely determined by the boundary conditions on H and K. That's the correct statement. The boundary conditions for H and K uniquely define the solution, but the solution depends on lambda. So you are above the bound for non-zero lambda, but then at weak coupling, you saturate the bound. Now, there are subleading corrections to this asymptotic solution, which are exponentially suppressed as a function of the radius. So I just said that asymptotically at large radii, we have this kind of magnetic monopole, right? We have the magnetic field at infinity. It just looks like a magnetic monopole. But if you come closer to the solution, then you see that there are non-abelian corrections. It's no longer a monopole, but it's some complicated non-abelian configuration. Those corrections are actually exponentially suppressed. So there is a radius, there's a sphere of radius r, and the radius r0 is given here. It's given in terms of the coupling lambda divided by h bar. So there's this sphere surrounding the monopole at r0. Outside that sphere, we have a magnetic monopole with the non-abelian corrections exponentially suppressed, but inside the sphere, we have the full non-abelian configuration. Okay, so it's an abelian solution well outside R0, non-abelian. There's a non-abelian for inside. In fact, you can be slightly more precise. I don't know if this is the moment to look at the technical issue. Somebody just came in. No. Okay. Well, we're okay. Okay. Continue. Thank you. So you can be slightly more precise about this abelian U1 which emerges. So there's an effective gauge field for R larger than R0, which can be defined as the longitudinal component of the gauge field at infinity. And it is defined here, it's this A mu, which is defined as the component of the non-abelian gauge field basically along the direction of the Higgs field. And the Higgs field here points in the radial direction. And then there is an F mu nu associated with that. So an effective Faraday tensor, which has the following feature. It satisfies the usual Maxwell equation, but it is not closed. It does not satisfy the Bianchi identity because it has this additional piece in terms of the Higgs field. And so this non-satisfaction of the Bianchi identity is quantified by defining a magnetic current. So you can define a magnetic current, which is the Hodge dual of this Faraday tensor, and it's defined here in the middle formula, and it's given purely by the Higgs field. Now you see all these epsilon tensors floating around. It's a lot of indices in both the group indices and the space-time indices. Not really important, but what is important is that this magnetic current is conserved, is identically conserved, but it is not a Noether current. You cannot derive it from any symmetry of the Lagrangian. You can use it to calculate the magnetic current. So the magnetic current is given in terms of this current in the usual way by integrating over a three-sphere over the entire volume, integrating the zeroth component, the time component of the current. And it actually reduces to simply an integral over the sphere at infinity using Stokes' theorem. What you see here, if you are familiar with this, you can view this. Actually, the result of that calculation is again an integer number divided by the electric constant. What you see here, apart from the normalization, this is actually a degree of the map. So that what you see inside the integral is an expression which, for a map between two spheres, computes for you the degree of the map. So if you have two spheres and a map between them, this map could have a degree. So it could be a map, it could be a one-to-one map, but it could wind twice or three times around the sphere. This is what this integral calculates. All right, a summary of what we have seen so far for the monopole. It is a solitonic solution. It's a non-abelian configuration of the Yang-Mills Higgs field. It has a non-abelian core of radius R0, but outside this core, all the non-abelian structure is suppressed exponentially, and we are left with a configuration that has non-zero electric charge, and which has the magnetic charge of a Dirac monopole. There is an effective or emergent U1 gauge field defined in terms of the non-abelian fields. The U1 gauge field, it's effectively satisfies the Maxwell equations, but not the Bianchi identities, and therefore it is an honest monopole solution. This violation of the Bianchi identities is just what you expect from a monopole, and it is expressed by a conserved topological current, which is a non-Noether current. It doesn't correspond to a symmetry, but rather it's a topological current because it computes the degree of a map. Its charge is an integer number, which gives the degree of the map from the sphere to itself. Yeah.
Can you say something more about the last point? Explain it better what does mean non-Noether current and the topological.
Yeah.
Yeah. You can make a simple example.
Yeah, that's a good point. And for that, I think the best is I go back here because there's quite an analogy with the Bostonization example. So in this case, we saw that we had a U1 symmetry in the Theta model. This U1 symmetry gave us a Noether current, and that corresponded to a topological current on the other side. So the topological current here in 2 dimensions was actually, it looks, formally it looks similar to what we just, so only that in 2 dimensions, there are fewer indices, so we only have one index. And so in this case, also this topological current actually depended on the values of the field at infinity, at plus infinity and minus infinity. And what the duality did is interchanged that topological current in one theory with the neutral current in the other theory. Now here, for the analogy with the 't Hooft-Polякov monopole is quite close. Of course, I haven't told you what is the electric dual of this, but the idea is that also here we have, so we have a topological current in a similar sense, so we can simply define this topological current like we did for the bosonic two-dimensional case, which nevertheless doesn't correspond to any underlying symmetry of the theory. And of course, the idea is that if there is some kind of, dual electric charge that this current then might correspond to a neutral current on the other side. That we yet have to. And so the idea is going to be that this magnetic charge, which is an integer and which satisfies the Dirac quantization condition, is going to be mapped to an electric charge on the other side. So that's and that will be the conjecture in n equals 4 super-Yang-Mills here. So that is yet to be seen. But that's how this example kind of fits into the previous examples that we did before. Okay, so I think this is a nice, a natural step to now S-duality in quantum field theory. And this really started with the Montonen-Olive duality conjecture. So when 't Hooft and Polякov discovered monopoles, there was a flurry of work on this kind of ideas, including this idea by Montonen-Olive, which we now know is not true. At least the original conjecture is not true, but there have been improvements of the conjecture, which seem to be true. So there are three elements leading up to this conjecture. First, the idea of electric-magnetic duality, which we have already discussed. Then there is the Dirac quantization condition, which is invariant under this duality. As you can check, because if we exchange E and G, the only difference is a minus sign, but since n is arbitrary, we just need to map the positive ends to the negative ends, and then the Dirac quantization condition is preserved. So this is a strong hint that there is that the duality is at work here between electric and magnetic charge. And then the third thing is the solitonic nature of the monopoles, the way they are realized in quantum field theory, not as Dirac strings, singular solutions, but rather as solitons. And we already know from our experience with other field theories that often we have these dualities between solitonic solutions and elementary excitation. So that gives us some chance that there might actually be a duality between the 't Hooft-Polякov monopole and normal electric charges. So what they conjecture is simply that the Georgite-Glashow model, the SU2 model, that it would be invariant under electromagnetic duality. Now that conjecture is incorrect, has been shown to be incorrect for ordinary Yang-Mills-Higgs models. The reason is that the spins don't work out. So the spin quantum numbers of the monopoles do not match with the quantum numbers of the electric solutions, that the particle excitations that we have in the Georgite-Glashow model. On the other hand, this conjecture is believed to play some role in QCD and is believed to be true in n equals 4 super-Yang-Mills theory. To introduce, so I want to go into n equals 4 super-Yang-Mills theory, not in any detail, of course, because Johanna is already speaking about that, but I need to say something about supersymmetry, kind of really a baby version of the idea of supersymmetry, just to fix some of the notation that I'm going to use. So as you know, supersymmetry is a symmetry that relates bosonic and fermionic fields within a given theory. So it's an extension of the Poincaré algebra generated by the displacement operators P mu, the Lorentz transformations, and also a new class of anti-commuting generators that we add to our theory, which I call Q. And Q acts on the boson states to give us a fermion and vice versa. So a theory is supersymmetric if and only if the action is invariant, or I should say, if the action is invariant under the transformations of the supersymmetry algebra. The if and only if would come if we talk about equations of motion. Normally we talk, there are some theories that don't have a Lagrangian principle. But for us, we will think about Lagrangian fields. So a prerequisite for that is that the number of physical bosonic and fermionic states in the theory must be the same, of course, because that's just from the definition that we have up here, right? Every boson must be matched by the symmetry to a fermion. So therefore, by counting, they must match. Depending on how many Qs you have. So if we want to make the usual Yang-Mills theory, SU2 Yang-Mills theory supersymmetric, SU2 Yang-Mills theory is not supersymmetric. It just has a gauge field. It's a theory for pure gauge field. If you want to make it supersymmetric, you need to add fermions to the theory. So the fermions, I will call them lambda. They are, I will introduce them to be real fermions, so real spinors. So Majorana fermions. You can define those in 4 dimensions. So this is the action that you get. This is the minimal supersymmetric action for Yang-Mills theory in 4 dimensions. So you get the usual action for the gauge field, and then you have this usual action for the fermions. Now the algebra, as it acts on the fields themselves, takes this form. It's a graded algebra. So when the supersymmetry generator acts on the A mu, then it gives you a fermion. When it acts on the fermion, it gives you a boson, namely it gives you the F mu. So that's exactly what we expect. Now, like I said, this is a theory of a single Q, a single supersymmetry algebra. You could add more Qs, which means you have more supersymmetry generators, which means for every bosonic state, you could have several fermionic states, depending on which Q you use. So this is what is called N-extended supersymmetry. So the supersymmetry charges, now there are several of them, and they form a closed algebra amongst themselves. They form an algebra not just with the Poincaré generators, with the usual Poincaré algebra, but also amongst themselves. This algebra, normally you would get 0 here. So these are anti-commuting numbers, so the right hand side should be 0. But you can extend the algebra by a number, what is called a central charge, which I will call Z. So Z is a numerical. It's not an operator, but it's a number. And this is still consistent. You can enlarge the algebra in this way, and that is still consistent with all the symmetries of the theory. So these Z's are the central elements of the algebra. They commute with all the generators of the algebra. Now, in the case of, but you have to be careful, you cannot add too many of these Qs, because depending on how many Qs you add, you might get unwanted states. For example, you might get gravitons if there are too many Qs, or you might get some other types of states. So you need to add the right number of states. In the case of n equals 4 super Yang-Mills theory, so where you add 4 Qs, there is 1 gauge field, and now you add, because you have 4 Qs, you also have 4 fermions corresponding to that 1 gauge field. So for each gauge field, you have 4 corresponding fermions. But you see that the number of degrees of freedom don't match, right? We have 1 fermion, 1 boson, which has two on-shell degrees of freedom, namely the two polarizations of the spin 1 field, and we have 4 fermions. So that doesn't matter. There are too many fermions now because we added 4 qs. To match up for that, we need to add more bosons. How do we do that? We do that in the minimal way by adding scalar fields. How many scalar fields do we need? We need 6 scalar fields. And probably you have heard this already from Johanna. So we have a total of 8 bosonic scalar fields. So 2 for the 2 polarizations of the gauge field, 6 scalar fields, and then 8 fermionic fields, which are 2 for each fermion times 4 fermions. So in this way, the bosonic and fermionic states matches, and we can consistently do that. So that's how to build a supersymmetric theory. How to build this n=4 supersymmetric theory with the right kind of state. Now let's look at what is the meat of this theory for dualities. So the claim is going to be that this theory is self-dual under S-duality. Remember that yesterday we introduced the notion of self-duality, saying that it is a duality that relates a theory to itself, but at a different value of the parameters. We need to check that the spectrum is invariant under the duality. So we need to know what are the states of the theory. Now, we already did that. There are 8 bosonic states and there are 8 fermionic states. But, and this is important, these are perturbative states. How did we get those states? Well, just by looking at the action, looking at what are the fields in the action. But we would not find the solitonic states in this way. Because to find solitonic states, we need to look at nonlinear solutions. So here we looked at, in particular, the polarizations, right? So that entails looking at on-shell states, looking at solutions of the free theory, and looking at the polarizations around that. But that's not what we do for solitons. For solitons, we look at the full nonlinear theory, and there we might find something completely different. So we need to learn something about the solitons of this theory. Now, it so happens that the central charges contain information about the possible solitons. It turns out that the quantum numbers of these solitons are given in terms of these quantum numbers, of these central charges that appear in the supersymmetry algebra. So the spectrum can be determined exactly from the algebra. So the algebra, the supersymmetry algebra, is so restrictive that it basically restricts the kinds of fields, the kinds of excitations that you can have. To do that in practice, one thing you can do is, rather than looking at the full non-perturbative theory, you look at the Higgs sector of the theory. That means the sector where you give the Higgs field an expectation value. That means one of your scalar fields, which is the Higgs field, will have an expectation value. So let's look at the spectrum there. Then we have, what is the spectrum there? And this is a calculation that was done by Olive and Witten. The spectrum that we find from the supersymmetry algebra, so the spectrum of solitons, is that we have one monopole with spin 1. We have 5 monopoles with spin 0. And we have 5 monopoles with spin 1/2. So those are the quantum numbers that you find from the central charges, from the supersymmetry algebra. As you see, that matches with the elementary particle spectrum after we do the Higgs mechanism. Because we said we had one spin 1 field, the gauge field, we still have that. We had 6 fields, but out of those, 1 is not there anymore because it's the Higgs field that has an expectation value. So we're left with five spin zero fields, 5 bosons with spin 0. And then we had 4 fermions. So that spectrum precisely matches. So we see that the spectrum is invariant, at least at this kind of numerology level, it's actually invariant. So there is a good chance. So this is different from the Georgi-Glashow model. In the Georgi-Glashow model, this already goes wrong. This step already doesn't work out. So it is precisely because we have the n=4 theory that this works out. So that's a first hopeful sign for this theory. But it's of course not enough. We need to know something about the dynamics. What do we have about the dynamics? Well, we can calculate the masses of these monopoles. And again, those masses, you can derive them from the supersymmetry algebra. So they are given by the BPS bound. So the supersymmetry algebra gives you the mass of these monopoles in terms of the Higgs expectation value and in terms of the electric and magnetic charges. So what you see is that if you exchange the two, if you exchange E and G in the usual way, the mass remains invariant. So the masses of the electric and magnetic charge are invariant under the duality. So that's another piece of evidence that this duality is on the right track. This is something that you cannot even begin doing with the Dirac type of solutions because we don't know the mass of those solutions. Here it comes out naturally of the Higgs mechanism. So let me say a bit more about what this S-duality then looks like. What is this exchange of the electric and the magnetic fields that we are talking about here? Now, this coupling constants E and G, how do they come in? Well, in Yang-Mills theory, you have 2 possible coupling constants. We have the electric charge E, it's the usual one in the action, in the Maxwell action, which is now the Yang-Mills action. That is the coefficient of the F wedge F term in the action, the usual coupling constant in the action. There is a second coupling constant that I already mentioned yesterday, which is what we call the theta angle, which is the coefficient of this topological term that we can add to the theory, which is the F wedge star F term in the action. That's a term that's a topological term because it's a total derivative. And like yesterday, we did this yesterday in the context of a very simple abelian Maxwell theory. Now we do this in the context of n=4. They can be combined into a single complex coupling constant, tau. And then S-duality takes the following form. It generalizes to SL2Z invariance, which acts on tau in the following way. It acts as fractional linear transformation. So ABCD is a matrix in SL2Z, so it's a 2x2 matrix with integer entries. And then tau acts, it acts on tau by this fractional transformation. Why is this useful, this language? Well, this might be reminiscent to some of you to how this is the modular group. So this is how the modular group acts on tau if we think of tau as the complex structure of a torus. Now there's no torus here, but this is where this kind of language or formulation comes from. So in any case, it's a fact that you can rewrite the action in terms, the n=4 action in terms of this coupling, and then the electromagnetic duality will take this form. So we have a duality of states. If the duality is true, which we don't know, we have some hints that it might be true and some checks, but we haven't done a full calculation yet. So we have a duality of states and of quantities. namely quantities at different values of the coupling, that is equivalent for the dynamics because it interchanges these different kinds of solutions. So the status is that there is strong evidence for S duality in n = 4, but the mathematical status still remains a conjecture. Okay, so that's what I wanted to say about n = 4, and this will come back, some of this language will come back in string theory. So now I'm going to introduce strings and d-branes in a kind of slow-paced fashion. So that's going to be the second part so that we can go on to the formulation of string dualities, and some of this background will play in that. So what is the foundational, so now we kind of start from zero. What is the foundational idea of string theory? Well, the foundational idea in the formulations in the late 60s and 70s by Nambu and Goto and Polikov and some others. Of course, string theory had come out of a different programming in quantum field theory about dual resonance models. But for our interest, the foundational idea is that particles, which are one-dimensional objects, right? They are point-like objects that move in space. Now, rather than having particles, we should generalize that to having strings, so to having one-dimensional objects, so one dimension in space, so 1 + 1 dimension in space-time. So rather than sweeping out a one-dimensional world line, now the string will sweep out a 1 + 1 dimensional, what we call a world sheet. So the motivation for that, from our standpoint today, is twofold. I would say. I mean, there are many more motivations actually, but one of them is string theory contains gravitational excitations in its spectrum. So if you look at the spectrum of the string, you automatically find the graviton in there. So obviously that is quite interesting by itself. The other thing is that in addition, the ultraviolet behavior of this theory is optimal. Unlike quantum gravity itself, if you attempt to quantize GR just by brute force, then you find that it is at one loop it can be made finite, but at two loop it cannot. That's the work of Ethoft and Feldman in 72, 73. That behavior is cured in string theory. So far as we know, the divergences can be renormalized. Also, string theory, the string is the sweet spot from another dimension that you might say, well, why not membranes or why not higher dimensional objects? The point particles are not good because GR is not good for quantization. Why not membranes? Well, it turns out that membranes and higher dimensional objects also cannot be quantized. They have infinite degrees of freedom. That will become important later. So strings seem to be the sweet spot between particles, point particles, and GR that is associated with them, and these higher dimensional objects. So the UV behavior of string theory seems to be much better. However, there are a number of things to be noticed. First, that string theory itself has some unphysical results. If you just take it on face value, you will find, if you work out the bosonic string theory, you will find tachyons or solutions with negative mass squared. And so you require a series of constraints.
Sorry.
Yeah.
The second statement here, there is literature, a lot of literature of this topic. It is you state that object with more than one dimension have ultraviolet behaviors that is highly problematic. So we are quite sure that it must be excluded from our.
Yeah, I will actually come back. That will be an important point in the M theory proposal. So we'll get back to that. So actually, we are, in that sense, we are. There is still a chance that we might quantize membranes. Okay. So there are only 5 consistent string theories that we know. And also the number of space-time dimensions is fixed to be 10. So if you want to have a consistent string theory, this seems to be what you need to do. There are other examples where you don't need to go to 10 dimensions. There are, for example, topological string theories, but those are quite special examples. So for the ordinary string theories, this is what you need. So how do we know that there are these 5 theories? Well, let's look classically. So we said, okay, we have a one-dimensional extended object. So it has a finite length in principle. So there are 2 options. It could be open or it could be closed. So let's now quantize this object. Now it turns out, as I already said, that if you quantize the closed string, so the closed string has the topology of a circle, then the excitations of the closed string contains the graviton. Okay, that's good. But then it turns out that not all theories have open strings. So the different 5 theories depend on whether you allow open strings or not. So the first theory is the type 1, which is the most non-trivial one, which is the one that you get if you allow for open strings. If you have open strings, then automatically you also have closed strings, because closed strings can always, open strings can always join to form closed strings, and so they can always, so you need them to interact. And so if you have open strings, then you also have closed strings. That means you always have gravity. The type 2 theories are the theories where you have closed strings and you don't have open strings in those theories. There are 2 kinds of closed string theories. There's the type 2A and the type 2B, and those are defined by the chiralities of the fermions. I won't go into that, although this distinction between 2A and 2B will actually be important, but later on I will specify how you can see this difference. Okay, this is the basic case, right? Just determined by open or closed and by the chirality of the fermions. Then there was this other theory discovered, the heterotic string, which in some sense is a mix of the 2. It's a mix of, it's a hybrid between a bosonic string and the superstring. It is a historically quite important theory, but I'm not going to use it here. In fact, I won't use the type 1 theory either. So I will here focus on the type 2 theories, which is where most of the work has happened in the past few years as far as dualities. Well, I should stress that dualities really came up also from the relations between the type 1 and the heterotic strings. But for the sake of definiteness, I will not do that. So already before 1995, which is now in hindsight seen as what we call the second superstring revolution, there were already hints that these 5 superstring theories are related by dualities. So it is clear that the second superstring revolution hinged, among other things, on the existence of duality. So what did the revolution consist in? Well, on several things, but for the large part in the fact that you now have these dualities connecting the 5 theories. So what happened in 95? There were 2 papers, 2 main papers, one first by Hall and Townsend, and then 2 months later, one by Witten, that gave evidence for the existence of a series of dualities that relate to 5 string theories and 11-dimensional supergravity. That's 1. This knowledge of dualities was combined with Polchinski's work on D-branes. Polchinski, together with two others, had worked already in 1989 on these objects called D-branes, but nobody, I mean, there hadn't been like a search of work. D-branes had been there always on the background. But now in 95, Polchinski and also Michael Green and others realized, when they heard Witten's talk at Strings 95, they realized that D-branes needed to be part of the picture of dualities. So Witten in 95 conjectured that there should exist a suitable 11-dimensional theory, which was dubbed M theory, that explains the existence of these dualities. So these dualities cannot be properly understood unless, to say it another way, what these dualities hint at is the existence of an 11-dimensional field. So, and this goes in two basic steps. So Witten's paper, I will now lay out the logic of this revolution in 95 in two main steps that were in Witten's paper. So this is my own kind of retrospective analysis of what Witten was doing in his paper, combined with other information. So Witten's proposal began from his discovery that among the lowest energy states in string theory, there are relevant. There are some states that are relevant when the string coupling is large. So normally we look at low energy string theory, and we also look at low coupling states, so weakly coupling states in low energy. Now Witten looked at low energies but strong couplings, and there he found that there were some additional states that people haven't really considered before as being straight states of string theory. What are some of the properties of these states? Well, these states, they are called BPS states because they saturate the BPS bound that I showed before. So precisely the Bogomolny-Prasad-Sommerfeld bound that I showed before for the monopoles. So they saturate that bound. They have a charge which is n divided here by the string coupling rather than the electric charge. The electric charge is now sort of given, is the string coupling. So, so superstrings, of course, carry electromagnetic fields. That electromagnetic charge is of the superstrings, I mean, to which the superstrings carried is measured by the superstring coupling G sub S. But this charge N here does not coupling to the string worldsheet. You don't see it in the string worldsheet because at string coupling GS goes to 0, and so these states are infinitely massive, and so they are invisible to the string worldsheet. So at weak coupling, these states are very massive. So, and you don't see them in the string worldsheet. On the other hand, they will become visible at strong coupling because at strong coupling they will have low mass. So therefore they are non-perturbative states. Their characteristic charge was dubbed Ramon-Ramon charge because it has some of the same properties of the magnetic charges of for example, the monopole, and it is called Ramon-Ramon charge because it couples to a certain type of electromagnetic field, which is not the usual electromagnetic field of the superstring, but it's an electromagnetic field that arises in a different sector of the superstring, which is called the Ramon-Ramon sector. Was there a question or a remark? No, I thought. Okay, so for that reason, because the specific electromagnetic fields that they couple to are these Ramon-Ramon fields, they are also called Ramon-Ramon states. So they are Ramon-Ramon BPS states. So that's the first step. The first step is, well, look, In string theory, there are these states which nobody has really looked at before. Here is their mass. They are non-perturbative, and they couple to these Ramond fields. Now, these Ramond fields were known before in supergravity, so we knew about their existence, but we didn't know really about their significance for string theory in this way. The second step is to connect this with duality. So we then said, well, this is a strongly coupled problem. It's a hard problem. These Ramond fields, we don't really understand them in this theory. So how can we make this into a tractable problem? Well, do what we always do a duality transformation. Go to weak coupling in some dual regime. So he remarked that the string theories, the strong coupling regime of some of the string theories could be explained, in particular, to be specific, these BPS states could be mapped to some other states at weak coupling, doing this duality transformations. So that was Witten's second step. Okay, so that's basically what happened. Now, to say a bit more about this duality, I will go again back to what we said before about the string, about the string worldsheet and how we define these electrical charges there. So remember that we said a particle action is a particle is a world line. It has an action that is given here. It is basically the geodesic length along the path of the particle. If we extremize this action, we get the geodesic equation. Now, for a string, we get something similar, but now the string, rather than having just the proper time or some affine parameter along its trajectory, if it happens to be a massless particle, now the string will have a two-dimensional world sheet. So it has two coordinates on this world sheet, which I call sigma. So sigma here has this index alpha, which comprises tau, which is the proper time on the string world sheet, but also sigma, which is the length of the string, right? So sigma is a segment. It's an interval if it is an open string, or it will be a circle, a closed dimension if it is a closed string. So alpha takes values 0 or 1 because those are the indices along the world sheet, while mu, which is the coordinate of x, so the coordinate of the string in the space-time, which is analogous to the location of the point particle, the little x mu there. Now mu goes from 0 to 9 because the space-time is now not 4-dimensional but 10-dimensional. So what this x is, this field x, it basically describes the embedding of the string world sheet in the space-time. It's completely analogous to the geodesic equation or the geodesic length of the particle. This coefficient here in front of the string world sheet is the string is called the string tension. It has engineering dimensions of mass squared or 1 over length squared. And for historical reasons, it's usually written as 1 over alpha prime, where alpha prime is called the Regis slope, which is basically, it basically gives you the spins of the different Regis solutions of the string, but that will not be important for us. So T basically gives the fundamental length of the string. Now, what is the equation of motion of this action? Well, it's a simple wave equation in 2 dimensions because it's box x, where the box is now defined on the string world sheet. So now let me take a single x, just one of these fields in space-time. it has a wave equation. Sigma goes from 0 to 2 pi. So here, what you see here is, here you see a circle, right? And then embedded in the space-time. So you have, in the vertical direction, you have that could be your time direction, and the spatial direction, that's the circle. The general solution for this type of equation, if you are on a circle, then it takes this form over here. So here's the center of mass motion, the x0. Then there is a linear term that gives you the momentum of the solution. Then there is another linear term in sigma that gives you the winding of the solution. And then there are a bunch of oscillators. These oscillators are, of course, the characteristic solutions of that wave equation, right? And you are familiar with this from just solving wave equations in any space-time. You always have oscillators that are sines and cosines. Then you always have this x0, which is just the constant piece. And then you have this linear piece, which gives you the momentum, or in this case, the winding. Now, notice that this winding term, this third term, which is linear in sigma, that is only non-zero if the corresponding space, if the corresponding string is a circle. Sorry, if the corresponding space-time dimension is a circle. Because otherwise, this would be a multi-valued coordinate. So this can, you see that x is multiply, if m is non-zero, this integer m is non-zero, then x is not uniquely defined, but it is defined up to 2 pi. So the only way to make this consistent is if x itself is defined on a circle. So that x takes an infinite range, but it is interpreted as being a circular direction. So it's compactified on a circle. Also from usual string theory, the momentum around the circle is quantized in terms of, so momentum around the circular direction is quantized in terms of the circular direction as n over r, so that the direction now, the solution now takes this form in terms of the momentum, the winding, and also the radial direction of the space-time. So I am now, so apart from considering the general solution for the string, I'm now considering a string compactified on one direction, because I'm going to go into T-duality in a moment. So I want to show how T-duality acts on this kind of solution. So we have seen that if our string is on a space-time that has a circular direction, then we have two kinds of modes. We have the momentum modes that give us the momentum of the circle, so the kind of center of mass, or the total momentum of the string. But we also have the winding of the string along the extra direction, along the circle. Now the mass of the solution, the mass of the string, can be calculated in this way in terms of n squared over r squared, and in terms of m squared r squared over alpha prime squared. And then there is a contribution from the oscillator, from the oscillators. Now what you see is that this solution, in this solution, the mass and also the field x itself, they are invariant under exchange of n and m, so under exchange of the mass and the winding, provided we also exchange the radius of the space-time to the dual radius, as you see here from the middle formula. So you see that from the top formula, if I exchange n and m, then I also need to take r to 1 over r with this factor of alpha prime. So this is an invariance of this class of solutions. The closed string spectrum of a bosonic string on a circle of radius r is simply identical to the closed string spectrum of a string on a circle of dual radius 1 over r. So that is the basic statement of T-duality. We can have a string, a bosonic string on a small radius, or we can have another bosonic string on a large radius. And the two are dual. And this might remind you of the isomol duality, where high temperature went to low temperature. This is somewhat reminiscent of that. Of course, the bosonic string is not good enough because it doesn't give you a consistent theory. So we need to extend this to the superstring. And in fact, you can do that. If you do that, because of the particular way that the fermions are defined, because of the chirality of the fermions around the circle, the conditions for the chirality on the fermions on the circle, whether the circles where the chirality is the same for the two types of fermions or different, you have the type 2A or the type 2B theory. And it turns out, and I will not go into that further, that T-duality exchanges the type 2A and the type 2B theory. So earlier I said that there were two type 2 theories, type 2A or type 2B. They differ by their chirality. And now it turns out that if you do T-duality, then in addition to exchanging those quantum numbers and interchanging the radius of the circle, you also need to change the fermions in such a way that the type 2A is exchanged to type 2B. So that would be the full T-duality map for type 2B, for the type 2 string theory. Okay, so that's the T-duality for closed strings. Now, how does this connect to D-branes? Because remember that D-branes were, along with T-duality, were a key part of the second superstring revolution. So Witten realized, okay, there are these dualities in string theory. T-duality was known before already, but now we need to incorporate D-branes into the picture of S-duality. That's what Polchinski did. So he discovered that closed string theories can also have open strings as long as they end on D-branes. So earlier I said, well, closed string theories, they are the type 2A to B theories, they only have closed strings because they are strings with gravity. There are no open strings. Now Polchinski says, well, we can actually have open strings as long as we have D-branes, because what is the problem? The problem is if you have an open string, the string has nowhere to go. So you need to fix it somewhere in the space-time. And this object to which you fix it needs to be dynamical. So that's what we call a D-brane. So that kind of object can now be defined in type 2B string theory. So that's a D-brane. It's you can think of it as a higher dimensional hyperplane that you have on your space-time, and your open string can end there, and thereby momentum can be conserved and all that. So what Witten now realized, together with Polchinski, is that the role of these D-branes is as follows. So there are states of closed string theory that are only seen at strong coupling. Those are the Ramon BPS states. I already said that before. Now these are D-brane states. So what Polchinski now realizes is that these are actually states of D-branes. So states where D-branes have a non-trivial charge, a non-trivial, non-zero Ramon charge. And also they are required to complete the picture of the Hilbert space and to complete the picture of the dualities between string theories, like monopoles in n equals 4. Earlier we said, well, if we want n equals 4 to be invariant under S-duality, we need the spectrum of electric particles and magnetic particles to match, and they did. We had these 16 states. Now we need the same in string theory, and it turns out that the missing magnetic states are precisely these D-brane states, which are defined magnetically. So the string gives you the perturbative electric states that you can define doing perturbation theory, The D brane states are the non-perturbative solitonic states that complete the picture to have duality. They are states of closed string theory, so they have a natural description also as black holes. And of course, that has been important later on. I mean, 1 year later, the developments went really fast-paced in the Strominger and Baffa story, and then later on Maldacena and many other people came along with these calculations of black hole entropy in string theory, the consequences for the black hole information paradox, and for further developments of string theory itself. So that came all out of this early work on dualities and D branes. So this is, in some sense, summarizing, and also what we said about D branes, and also saying slightly more about what kind of charges and what kind of electromagnetic fields you need. So we have said D branes are charged objects like the monopoles, but like the monopoles, their charge is not a neuter charge. It's not a charge that you find by finding a conserved quantity in the theory, but rather is the charge of a soliton. So it's a kind of a topological charge. It is called, this Ramon charge. So it's not the elementary string charge. So the elementary string charge is what we call the never charge charge, which is the charge that couples to the gauge field that you find in the fundamental string. Here, this Ramon D brane charge does not appear in the elementary charge, but it does appear just like the monopole charge in the algebra of supersymmetry. So they appear as central charges in the space-time supersymmetry algebra of string theory. And so since the supersymmetry algebra has to be realized at all values of the string coupling, the supersymmetry algebra is a guide to non-perturbative physics. So this is also part of what Witten now built into string theory. So at low energies, D branes can be described in supergravity, which is the low energy description of string theory. And the fields that you need to couple to the D brane, which appear in supergravity, are P forms. So they are not two forms or one form, like a gauge field is a one form and its Faraday tensor, it's two form. But now since these D branes are higher dimensional objects, you need P form. So where P could be 3 or could be 4, depending on the dimensionality of this object. So the dimensionality of the D brane, the number of dimensions along which it is extended, determines the rank of the form that you need. So that is fully analogous to what happens with point particles. So how do we know what is the charge of an electron? Well, the way that it shows in the Maxwell theory is, of course, in the usual way. You take a charged particle has a geodesic length, and it couples minimally to a gauge field that is on the space-time through the minimal coupling through this term over here. So the momentum couples to the gauge field, and that will show in your geodesic equation as a coupling between the geodesic equation and the Faraday tensor. That gives you an electric source for your geodesic equation. Now it is completely analogous, works completely analogously for the string. The string, we said it has a two-dimensional world sheet. The action is given here by the first term, by the Namu-Goto-Polikov form of the action. But then there is this additional term which couples to now not a one form, not a gauge field, but now this gauge field is a two form because basically the string world sheet is two-dimensional. So each of the dimensions of the string worldsheet needs to couple to the gauge field, and you see that because through the coupling here, just for technical reasons. And so that means that the field strength, so kind of the analogous of the Faraday tensor, will now be a three form. So a tensor with an antisymmetric tensor with three indices, what I call here H. So this is completely analogous to what we do for point particles, only that we have added one dimension. Okay, so now for D branes, DP branes, they couple to Ramon P+1 forms. So P is actually the number of spatial dimensions of your D brane. So a particle would be P = 0 because it has 0 spatial dimensions. It's a point. A string has 1 spatial dimension, so it has P = 1. A membrane has P = 2, and so on for higher P's. So now we will have a P+1 gauge field with kind of Faraday tensor field strength that is a P+1 form, which is the external derivative of the P+1. Now the Ramon field will contribute to the supergravity action in the usual way. So like in normal Einstein-Maxwell gravity, you have your Einstein-Hilbert action, and you have your Maxwell field that couples to it, and both interact in the Maxwell action. If you want to get, for example, a charged black hole solution, or solution for a charged object in space-time, in the same way, you can do that for a P brane, where the difference now will be that you get this P+2 form, and there is a coupling to the scalar field here. And there are some normalizations in front. Okay, so T-duality. So how do we fit these D branes into the picture of T-duality that we have before, with the exchange of the small radius with the large radius and the 2A theory with the 2B theory? Now, the idea is the following. Type 2A theory only has D branes of even dimension. So it has P0 branes, it has P2 branes, P = 4 branes, and so on. So it has point particles, it has membranes, it has 4 branes, and so on. The type 2B theory only has D branes of odd dimension, odd spatial dimension. So it has 1 brane, 3 branes, 5 branes, and so on. That is, again, for technical reasons. But that is how the two theories incorporate D branes. Now, for T-duality to be consistent with the existence of D branes in our theory, we need these different dimensions of D branes to match between the 2A and the type 2B theory, right? So we need T-duality of the D branes of even dimension in the type 2A theory to match to the D branes of odd dimension in the type 2B theory. Now, it turns out that that is exactly how T-duality acts on D branes. So if you have a D brane on a space that is compactified on a circle, like we did before for T-duality, but now also the D brane itself is wrapped on that circle, and you do the T-duality along that direction, which means you invert the radius like we did before, it turns out that if you do that for the D brane, it exchanges the boundary conditions of the strings on this D brane, exchanges them from open string conditions to closed string conditions. So it exchanges basically Dirichlet boundary conditions to a Neumann boundary condition. So that means the D brane which was wrapped along this direction is now no longer wrapped along the direction. In other words, it reduces the dimensionality of the D brane along that direction. So in other words, T-duality maps, say, a 5 brane of the type 2B theory to a 4 brane of the type 2A theory. Or it maps a 4 brane of the type 2A theory to a 3 brane of the type 2B theory, and so on and so forth. That is when you wrap your D brane along the direction. If you don't wrap the D brane along that direction, but do the T-duality along a direction transverse to the D brane, then it precisely exchanges then it increases rather than decreases the dimensionality. Okay, those are some details that we don't really need to go into the numerology here, but just to say that this actually works out, so that the T-duality is actually consistent with the introduction of D branes into the type 2A and the type 2B theory, and how those two theories incorporates D branes of different dimensionality. Okay, so now for D branes, we have D branes are themselves magnetically charged, and it turns out that electric-magnetic duality also acts on the D branes themselves. I'm actually going to skip that for reasons of time, so I will not mention that. So let me now, I now go to the last point, which is the effective dualities between the string theories and M theory. So far, we have seen, kind of to summarize the train of thought we started with, we developed these Solitons solutions, which we find in condensed matter theory, like the Sine-Gordon model and like the Thirin model. So these dualities exchange elementary particles with Soliton solutions. We were able to generalize those kinds of solutions to incorporate the magnetic monopole, and that is potentially important for the problem of confinement in QCD. Then we generalized this to supersymmetric theories, where in n equals 4, we have S-duality between electric charges and magnetic charges, and we saw that the duality actually works in that case. And then we moved on to string theory, where these dualities are incorporated also into the theory in various ways. And I focused in particular on the T-duality. So what the T-duality does, it exchanges a string theory on a small radius with a string theory on a large radius, and thereby it also exchanges D branes of different dimensionality. Now we want to look more, kind of go back to the big picture on dualities since 1995. So Witten realized that when we consider type 2A string theory at string coupling, as we are motivated to do by the consideration of D branes, because now D branes somehow are these solutions that are relevant at strong coupling, then this coupling can be reinterpreted as the radius of a hidden dimension, an extra 11 dimension that kind of pops up at strong coupling. And unfortunately, I cannot give the details here, but there is a numerical prediction for the radius of this 11th dimension given in terms of the string coupling. So it's the string coupling to the power of 2/3, and then you have to also incorporate the Planck length, the string length in there, but I set it to 1. So that's the prediction of string theory for the dimension for the radius of this 11th dimension. This can be obtained by Kaluza-Klein dimensional reduction of the Einstein-Hilbert action from 11 dimensions to 10 dimensions. So the idea is that you begin, you can do it both ways. You can start in 11 dimensions, in 10 dimensions, and go up to 11 dimensions. Or you can simply, and the way this prediction is made is you begin with 11 dimensions, you begin with Einstein, the Einstein-Hilbert action in 11 dimensions. You compactify it through the usual Kaluza-Klein reduction to 10 dimensions, and then you require that you get in 10 dimensions, you require that you get the Einstein-Hilbert action, that you get Einstein theory in 10 dimensions, but in what is called the string frame. So in the frame that is specific to the time to A theory. So in other words, you demand that you match the 11-dimensional theory with your low-dimensional string theory in 10 dimensions, with the kind of Einstein theory that you get there. That gives you this prediction. So that is what we call the massless sector of the theory, because we only have massless fields here, only the metric, only the dilaton, only if you include also antisymmetric fields, only massless fields. Now, this prediction was strengthened to include also the massive fields of the Kaluza-Klein reduction. You know that when you do Kaluza-Klein reduction, you get the easiest thing to get is the massless excitation, right? Because, but then you get also massive modes, because you know that if you have electrical fields on a theory that is on the circle, then or any kind of fields on a circle, then the momentum around that circle will give you additional states that are massive. And in fact, we already saw that in the T-duality, that we had this momentum around the circle. So here we get the same thing. We get these states which have mass, which are momentum states, with the momentum quantized in terms of the 11-dimensional circle. So these actually match up with the PPS states of the Ramon states of the B0 branes in type 2A string theory. We said in type 2A string theory, we have B branes of even dimension. In particular, we have point particles, so P0 branes. Those particles have a mass that you can calculate using Witten's formula. That is the mass. Now, that mass predicted by the D brane calculation in string theory is matched with the prediction of supergravity in 11 dimensions using the prediction of string theory for the radius. So those two things match up. So this is a further piece of evidence that the framework is consistent. Now, of course, you might think, and well, we have this 10-dimensional theory. We know that our fundamental fields are strings in 10 dimensions, but if we are in 11 dimensions, then what is the fundamental theory there? I mean, we know we cannot formulate strings in 11 dimensions. There is no such thing. We said strings only make sense in 10 dimensions. What is our candidate fundamental theory in 11 dimensions? Well, the answer is nobody really knows. I mean, that is still today an open question that people are working on, and there is quite a lot of work on this direction. But of course, we have some hints from this kind of prediction. First of all, we have seen 11-dimensional supergravity is somehow relevant here. So whatever theory we have in 11 dimensions, 11-dimensional supergravity should be its low-dimensional limit, right? Now, if we study supergravity in 11 dimensions, it turns out that this theory is quite unique. Unlike the string theory, so the string theory has a bunch of fields. There's the type 2A, there's the type 2B, there's the type 2-1, then there is the type 1. There's none of that in 11 dimensions. In 11 dimensions, you have a single supersymmetric supergravity theory. It is the 11-dimensional supergravity, which has a single gauge field, which is the free form. So it only has a free form, which has P equals 2. Of course, with a free form, with a P equals 2 electric magnetic field, that is associated with a supermembrane. So from the point of view of supergravity, almost the only thing we could have is a supermembrane. So we could have a supermembrane in 11 dimensions. So it is natural to expect that we might want to quantize the supermembrane in 11 dimensions and then reproduce the results of string theory in 10 dimensions. Unfortunately, this does not work quite as easily for the reasons we discussed before. This supermembrane cannot be quantized. To solve that, there are two proposals. The first one is the matrix theory proposal, which says that basically we should discretize this membrane. So this membrane is not itself fundamental, but is made up, it is the low energy limit of these D0 branes. So these D0 branes in 11 dimensions are now the fundamental objects. And what are these D0 branes? These D0 branes, so 11 dimensions, so M theory in 11 dimensions is actually the quantum mechanics of non-abelian D0 branes. So D0 branes defined in 11 dimensions. What do I mean by non-abelian? Well, these D0 branes, the coordinates of these D branes are basically n by n matrices, where n is the number of D branes. So if you have n D branes, then each D brane is a matrix. The coordinate of this D brane is a matrix. And there are non-abelian interactions between the D branes. So that's a matrix theory proposals, and there are various checks of that, including up to 2 loops. And with that, you can reproduce 11-dimensional supergravity. A second proposal is, no. And actually, you can also reproduce some of the membrane properties. The second proposal is to say, no, let's take the membrane, the supermembrane seriously, because we know, after all, we know that supermembranes classically do give you strings. If you take a supermembrane, you compactify it on this 11th dimensional circle, it will give you a classical string. In doing that dimensional reduction, there are actually some surprises, but okay, I won't go into that. But it does work out. So that's the second proposal. Let's take that seriously. But the extra ingredient to overcome the fact that a membrane cannot be quantized is the idea by Townsend, proposal by Townsend, is that, well, we should not have an elementary membrane. We should not think that the supermembrane is some type of elementary field, fundamental field that we should quantize in the usual way, but we should think of it in the usual way that we should follow the philosophy that we've been following right now. And by now you know what it is. We should think of a soliton. We should think of a solitonic membrane. So we should not add any type of source to our theory, but rather we should find a solitonic membrane. And indeed you can find such a membrane. And his conjecture was that such a membrane, because it is smooth, it doesn't have the instability of the other membrane. I can say more about that if people are interested, if there are any questions about that. So now you get, of course, there is much to be checked here. So these are conjectures. They have been checked. I mean, these are duality conjectures relating the different theories. So there seems to be a consistent framework. So far as I know, no inconsistency has been shown, but also there is not a mathematical proof, precisely because these theories are perturbative. So there is a self-consistent framework of dualities from 11 dimensions to lower dimensions. And also in this way, I did not have time to, maybe I will go into that. Actually, I think that's what I will do. I will list the rest of it for tomorrow. I will say more about it tomorrow, about how you can fit S-duality into this picture. So they have only talked about T-duality and about D-branes and membranes, which has to do everything between the relation between 11 dimensions and 10 dimensions. But we need to fit S-duality into the picture. So I will do that tomorrow. So to summarize, we have illustrated 3 features of dualities in some of our advanced examples. hard easy, which means weak coupling versus strong coupling, relating the Hilbert spaces within a given theory, and in particular the elementary particle states with the solitonic states. It works out beautifully for some of these quantum field theories, and we saw some hints that it also works in string theory, and it allows, assuming that there is such a duality, actually allows us to make some new predictions. The unification framework, which I will say a lot more about from the heuristic perspective on Thursday, is of course this M-theory conjecture, which I have presented here in some of its kind of basic contours. So that has to do with the idea of, okay, let's use duality to unify different string theories. And then finally, the idea that micro and macro, we have an exchange of Noether and topological charges and elementary and solitonic charges. So this is how, and so in this way, we illustrate within string theory the features and dualities.